We present a method for learning soft robotic tasks, such as grasp classification and state estimation, while simultaneously optimizing the placement of sensors to best solve those tasks. Previous work on algorithms for soft robot learning has often relied on external sensor data, captured, for example, from external cameras or motion capture systems. Our method works with intrinsic strain measurements like those captured from commercial off-the-shelf strain sensors. Further, our algorithm adaptively prunes a large set of candidate sensors down to an optimal set for the task at hand. A neural network which takes these sensors as input is co-learned with the sparsification procedure. Our core contribution is a neural network architecture designed specifically for soft robotics applications, which takes as input robot strain and strain rate information and processes this for efficiently solving user-specified tasks. A special neuron is used as the input to our neural network architecture, which stochastically drops out less salient sensor inputs to a target budget. The end result is learned sensor placements and network weights, which solve tasks better than methods with more naive sensor placements. As a first application, we demonstrate a dynamic in-hand grasp classification, in which a gripper must disambiguate between different grasp shapes. As a second similar application, we demonstrate the gripper's ability to disambiguate grasped materials of varying stiffness. Our method finds sensor placements that allow us to learn more generalizable classifiers for tactile sensing. Further, the sensor placements make semantic sense. They are primarily distributed along the interior sides of the gripper's palm and fingertips, where most tactile interaction takes place. Material stiffness regression is also possible. Here are the results of the material regression task, which shows high correlation between true and predicted material stiffness. Our method has much better results than the randomized baseline. As a second application, we demonstrate pose reconstruction of soft robots from only sparse strain and strain rate sensor input. As training data, we use simulation frames from a variety of soft robot trajectories. Here are some results. Sensors for biped tend to appear mostly in the legs, which house the biped actuators, and experience the largest deformations and deformation rates. Here is a 2D elephant with a highly dynamic trunk. Sensors for the elephant tend to appear mostly on or near the trunk, which experiences the most dynamic motion. This is a fixed base dynamic 2D arm. Sensors for the arm tend to appear closer to the fixed base at the bottom, which has a kinematic and dynamic impact on everything above it. Our method also works in 3D, including on this 3D hexapod. Here are some results. Our 3D arm is an analog of the 2D arm. Again, some results. Finally, this 3D quadruped is an analog of our 2D biped. The latent feature space can be used for understanding the natural coordinates of the soft robot, as well as a model for control applications. Thank you.